Hello students, welcome to this lecture 1 of this week, in which we're going to start reviewing the material to prepare ourselves for calculus. And the first part of review will be about real numbers, sets, and inequalities. All right, this is the first topic for the discussion that we're going to have. So first thing we're going to talk about, we're going to define real numbers. And we're going to start with integers. And the symbol for integers that we're going to use is this strange letter Z, which has a double line in the middle. And by integers, we usually mean the following numbers. So they start at negative infinity and they go by 1. So negative infinity, then negative 10, negative 9, negative 4, negative 3, negative 2, negative 1, important number 0, 1, 2, 3, 4, and so on. All right, so 3 dots usually in our class means it's keep going. All right, so we can take integers and we can exclude division. So if we rule out the division by 0, the division by 0, and we can create ratios of integers, of all possible integers, excluding 0 in the denominator. And this will make up the rational numbers. And for the rational numbers, the usual symbol is this letter Q with an extra line in the middle. So what would be the examples for the rational numbers? The examples would be like 1/2 would be there, 3/5 will be there, 17 out of 1,000 would be there, also number 9 would be there, right? All integers will be inside of it because we can think of 9 as 9 divided by 1. Another important part is that negative fractions will also be there, like -5/2 will be there. But we can also write -5/2 as 5/-2, and also we can write it as negative in front 5/2. So there are many different ways to write negative fractions. So this would be all rational numbers, basically the ratios of integers excluding 0 from the denominator. What happened with rational numbers in the old times? Greeks that are famous for their development of mathematics, they thought that all quantities in the world, all quantities can be represented by a rational number. So that's what they believed in. But what happened about 500 BC, Hippasus of Metapontum, it's a famous Greek mathematician, and his name is kind of hard to pronounce. And that is the place where he lived. and it happened about 500 BC. So what happened about this age? He built the following triangle. He put the length of 1 over here, length 1. He put the length of 1 over here, and he connected this triangle like this to build the right triangle of sides 1 and 1. But what do we know about 1 and 1? We will talk about it later in the semester, that this side will be square root of 2. And square root of 2 is irrational number. Right? You can look up the proof. It's a really interesting proof. It's not hard, really logical and interesting proof. If you're interested, ask me, we will prove it together. All right, so basically the belief that Greeks have that all quantities can be represented by a rational number is not true, because here is the side of the right triangle that is represented by irrational number. All right. So what we can do next, we can take all of the rational numbers. If we take all of the rational numbers and take irrational numbers, if we take those things, they would make up all real numbers, right? So rational numbers and irrational numbers together make up the real numbers. All right. So knowing this, what we can do with the real numbers? Real numbers are it is useful to represent real numbers by a line. All right, so we can create a line like this, and we can represent real numbers by this real line, right? So real line is a good representation of real numbers. And for real numbers, I didn't say it, but for real numbers, we can use this symbol R with a double vertical line. All right, so basically, to the right, we have a positive direction. And to the left, we have negative direction. And in the middle, we have origin. So how do we represent real numbers on this real line? So small rule that we make up is like this, with each real number, we can associate a point on the real line and now we make up our rule. So we say as follows, and we make up our rule, and we need 3 parts for this rule. First part for this rule says the following, that we associate we associate with each positive number R a point that is R units away from the origin. In the positive direction. In the positive direction. So that's our first part of the rule for the positive direction. And remember, we had also negative direction. So we can say that we associate with each negative number negative R a point that is R units away from the origin in the negative direction. All right, so we covered positive direction, we covered negative direction. The last part of the rule has to cover the origin. So we associate the origin with number 0. So that's pretty much it. Now we have a rule how to put the numbers on the real line. The last thing to add is just a comment. We say that the real number corresponding to a point on the real line is called the coordinate of the point, and the line is often called the coordinate line instead of the real line. All right, so how would it look in practice? In practice, it would look something like this. You have a 0, you have positive numbers going to the right. So for example, square root of 2 will be between 1 and 2. Then negative 1, negative 2, and here we'll have a negative 1/2, for example, and so on. All right, so this way we defined real line, we defined real numbers. What else should we say about this real line? Small rule, which is really important to us. Real numbers are ordered. And I have to notice that not all kind of numbers are ordered, like complex numbers are not ordered. So what does it mean, ordered? That means that given any two real numbers A and B, we have exactly one of the following. Is possible. So what is possible for two numbers A and B? First thing that is possible is A is less than B. So number A is less than B. Second thing that is possible, B is less than A. And the last situation that is possible is that A is equal to B. So only one of three is possible. A is less than B, B is less than A, or A is the same as B. All right. So I said less than B, and I said B less than A, and A is equal to B. And I didn't really define it, so maybe we can create a small definitions for these meanings, right? We can say that if A and B are real numbers, then what does it mean A is less than B? A less than B means that if you take B, which is a bigger number, and subtract A, the difference is positive. The difference is positive. Second thing we should define, what is A less or equal than B? This means A less than B or A is equal to B. All right. So we created these two definitions. Couple more things to add. One of the things that we can add, geometrically, we mean that A is less than B. What does it mean geometrically? Geometrically, A less than B means that B is to the right of A. And another thing that we should add here while we're doing this, we can say that we can write A less than B as B greater than A. It's the same expression. All right, so what would be a couple of examples for these ideas? Couple of examples. We know that 5 is less than 9. We know that. We also know that 11 is bigger or equal than 4. Why it's bigger or equal than 4? Because according to the rule, it could be it could be that A is less than B or A is equal to B. And we know that 11 is greater than 4, so it's also greater or equal than 4. And also we know that 6 is greater or equal than 6. Why? Because 6 is equal to 6. Therefore, it's greater or equal than 6. So the first theorem of the semester that we're going to talk about is a theorem that helps us solve inequalities. It helps us solve inequalities, and the theorem goes like this. First part of the theorem says that if A is less than B and B is less than C, then A is less than C. And this property is called transitivity. All right, if we have two inequalities in a row, A is less than B, and you can see that there is a match between this B and this B, and B is less than C, therefore A is less than C. And second part of this rule of this theorem says that if A is less than B, then A plus C is less than B plus C. So that tells us that we can add the same number to both sides and the inequality stays in the same order. Okay, so the next rule that we get is part C, that says the following. If A is less than C, I said C is less than B, sorry, then what? Then A times C is less than B times C when C is positive, and A times C is bigger than B times C when C is negative. So what does it tell us? If we multiply both sides by a positive number, our inequality stays the same, but if we multiply by a negative number, we have to reverse the sign of the inequality. And now part D of this rule says that if A is less than B and D is less than C, then A plus D is less than B plus C. So basically, if inequalities go the same way, we can add the left side and we can add the right side, and the inequality would stay in the same way. And the last part of this rule says that this is a part E. If A and B are both positive, or both negative, and A is less than B, then 1 over A is bigger than 1 over B. A short example for this is, first it makes no sense, but let's look at it. If we have 2 less than 3, this would mean that 1 over 2 is bigger than 1 over 3, because half is bigger than a third. And one big note for this rule, note is the following. In the previous theorem, if you replace strict inequalities, strictly less or strictly greater, with less or equal or greater or equal, respectively, the theorem will be still true. Is still true. So this is a big note. So basically all of the rules that we discussed, A, B, C, D, and E, would be true if we replace strict inequality by non-strict inequality. All right. So let's do a few examples. First example is if we have that A is less than B and B is less than -1, this would imply that A is less than -1. And for implies, we have a special symbol in mathematics. So slowly, I will start introduce symbols. This symbol means implies. So equal sign with an arrow at the end. All right. So this was rule for part A of the theorem. The second example is if -2 is less than -6, we can add 5 to both sides. To get -2 plus 5 is less than -6 plus 5. I said -6, this is wrong. Should be +6, otherwise it would be a mistake. So -2 is less than 6, and if we add 5 to both sides, we're going to get on the left side, we're going to get +3 is less than 11. All right. So basically, -2 is less than +6 is equivalent to +3 less than 11. All right, so then example number 3 says that if we have -4 less than 9, we can multiply both sides by 2 to get -4 times 2 is less than 9 times 2, and on the left side we get -8 is less than 18. We can also take the same expression, -4 less than 9, and multiply both sides by -3 to get -4 times -3 is bigger than 9 times negative 3. And if we calculate it, we're going to get positive 12 is bigger than negative 27. All right, and example for the rule number 4. So example number 4 says that if 3 is less than 6 and negative 8 is less than 4, we can add together. We can add together the appropriate sides. To get 3 plus negative 8 is less than 6 plus 4. And if we evaluate it, we're going to get negative 5 less than 10. So last example for the last rule in the theorem says that if 5 is less than 13, this implies, again, this symbol means implies, and we're going to use it often this semester, so try to remember it. 1 over 5 is bigger than 1 over 13. All right, so probably a good place to stop this lecture 1, and I'll see you in the next lecture.